So let's see the answer of questions regarding the selective precipitation using the pH. Last time we ended the question 24 if I remember, and now today we are starting on question 25. Let's see what question 25 is saying, because last time we have seen how the selective precipitation works. And now today we are going to see how we can control the pH so that you can have a selective precipitation of one ion without precipitating the other ion. Question 25 is saying a solution contains 0.01 molar of calcium and 0.01 molar of lanthanum ion. Then they are asking what concentration of the HCl of the acid which is needed to precipitate lanthanum without precipitating the calcium. If the concentration of oxalic acid is 1 molar, so that means the concentration of oxalic acid was given as 1 molar. They have given also the KSP values for a calcium oxalate and the KSP value for lanthanum oxalate. So we have the pK1 for the oxalic acid, which is equal to 1.25, and you have pK2 for oxalic acid, which is 3.81. So here they are asking what is the concentration of the acid which is required so that you can only precipitate the lanthanum. So how do we proceed for this kind of question? What we do, we just find the concentration of oxalate to precipitate the lanthanum, and also you find the concentration of oxalate ion to precipitate the calcium. Then after finding this concentration, we make sure that because they are asking the only to precipitate the lanthanum, so we make sure that the concentration of oxalate does not go beyond the concentration to precipitate the calcium. So what you do, we find the concentration of the oxalate required to precipitate the lanthanum. To start precipitating lanthanum, we also calculate the concentration of oxalate ion which is required to start precipitating the calcium. So then what we need to do, because we want only to precipitate the lanthanum, we make sure that the concentration does not go beyond the concentration which are required to start precipitating the calcium. So that is how we proceed. Let's go and see how we can calculate the concentration of oxalate required to precipitate the lanthanum and the concentration of oxalate required to precipitate the calcium. Of course, we need to rely on the KSP values. Let's see. So this is the expression. Then we will be getting 3 more of lanthanum in dissociation. Then you be having also 3 more of oxalate. If you are writing the KSP expression, then you need to raise the power of 2 because we have here 2 moles, and here we need to do raise to the power of 3 because we have 3 more of oxalate. So if we are doing the dissociation of calcium oxalate, also we need to write the KSP expression. Then we will get this KSP expression. Then we can determine the concentration of oxalate required to start precipitating the lanthanum. So then here we are going to replace the KSP its value. So this is, we replace the KSP. We also replace the lanthanum concentration. It was given in the question 0.01. Then we calculate what will be the concentration of oxalate required to start precipitating the lanthanum. So we do the rearrangement and the calculation, and then we find that this concentration will be equal to 2.93 times 10 power negative 8 molar. This is the concentration of oxalate required to start precipitating the lanthanum. So after this concentration, the lanthanum will precipitate, and then when calcium will start to precipitate, then we stop. So we need to make sure that we are not going to add too much oxalate so that we can also precipitate the calcium. So now what will be the concentration that is of oxalate required also to start precipitating the calcium so that we don't go beyond that concentration. So we also calculate and we find that the concentration of oxalate, which is required to precipitate the calcium, will be equal to 2.32 times 10 power negative 7 mole. Of course, here we have written the expression, and then we replace the Ksp and the value of calcium, and then we determine the concentration of oxalate required to precipitate the calcium. So that means, so we need to make sure that the concentration does not go beyond this one, because after this concentration, then you will be precipitating also the calcium, and you won't need the lanthanum to precipitate. That means we need to make sure that the concentration of oxalate does not go beyond this one, because below this one only lanthanum is precipitate. But if you go above this one, that means we are also going to precipitate the calcium. So that means you can see here we have 10 power negative 8, because lanthanum requires concentration of oxalate to precipitate fast. Then we need to make sure that we don't also precipitate the calcium by controlling that the concentration required to start precipitating calcium does not go beyond this one. It stays like this one, but not go beyond this one, because beyond this concentration we will be precipitating also the calcium. So now how do we do? So to keep this concentration, we need to make sure that we control the pH. So we need to control the pH so that the concentration of oxalate in the solution stays as 2.32 times 10 power negative molar. Because at this concentration, after this concentration, we are also going to precipitate the calcium. So we need to control the pH. How do we control the pH? We calculate how much of the hydrogen in the solution, or how much of the acid we need to add, so that the concentration of oxalate stays at 2.2 times 10 power negative 7 molar. So how do we proceed? So here we have the oxalic acid in the solution, which will be dissociating to give H plus and this one. Then this one is also going to dissociate to give H plus and this one. Then we calculate how much H plus are required, or how much H plus will be added, so that the concentration of oxalate stays as 2.32 times 10 power negative 7. So what we are going to do, we are going to have the overall reaction. So we add them, the two together, the dissociation of the oxalic acid. So we cancel this one, and this one also we cancel because they are the same. Then you write the overall reaction. So it will be remaining of this one, and then it will be remaining also this one, and also this one. So the overall reaction will be this one, which will give 2 proton plus the oxalate ion. Then how do we find the overall, the K value? Overall K value, we multiply the 2 value, multiply Ka1 times the Ka2. So then we get this value. Now, by having this value, we can write the expression of this K. We write the expression. So by taking this one, raised to the power of 2 times the concentration of oxalate dividing with the concentration of oxalic acid. This was given. This also, that's what you need to calculate, and then this was given. That means we need to make sure that this one does not go beyond 2.2 times 10 power negative 7, because we are determining what will be the concentration of the acid which is required to be into the solution, so that the concentration of the oxalate ion does not go beyond 2.2 times 10 power negative 7 molar, because beyond this concentration we are also going to precipitate the calcium, and we only want to precipitate the lanthanum. So how do we proceed? We replace the value of K that was calculated here. Then after we replace the value of the oxalate as 2.2 times 10 power negative 7. We replace the value of the oxalic acid in the solution. They told us that is 1 molar. Then we calculate the concentration of the hydrogen. So that means we need to make sure that the hydrogen in the solution does not go beyond 6.1 molar. If you control the H plus by controlling the pH to this value, in that case we are sure that we'll be having 2.2 times 10 power negative 7 molar as the concentration of oxalate into the solution. So that means we'll be adding the HCl, so that the H plus concentration in the solution is 6.1 molar. So that means if we do that, we will be sure that the only lanthanum ion will be precipitating and the calcium is not going to precipitate. Let's go to question 26. Question 26 is saying a solution contains 0.015 molar of iron and 0.015 molar of lead. Then they're asking what concentration of acid is needed to ensure the lead precipitate as the lead only without precipitating the iron. So the question is also like the one we came to solve. So we use the same way to solve this problem. So it was given, the Ka1 was given, Ka2 was also given, and also we have the concentration of the H2S. What we do, we just find the concentration of the S2 minus required to precipitate the lead. You also find the concentration of H2 of S2 minus to precipitate the iron. Then if we do that, of course we will be using the expression of the KSP. We will see that the concentration of the S2 minus to precipitate the lead will be equal to 5.3 times 10 power negative 26. Then we also determine the concentration of S2 minus required to precipitate the iron. We see that it will be equal to 4.2 times 10 power negative 16. So you can see that this one, lead is the one which requires less concentration to precipitate as compared to the to iron. That means this one will precipitate on the first time. So, but for us to precipitate on lead, we need to make sure that the concentration of the S2 minus in the solution does not go beyond 4.2 times 10 power negative 16 molar, because above this concentration also the iron will start to precipitate. So if you want to precipitate only the lead, we need to make sure that the concentration of the sulfur does not go beyond this one, so that we can precipitate the iron. We need to make sure that we are only precipitating the lead, not precipitating the iron. So we also do the same by calculating the concentration of the hydrogen which are required into the solution, so that only the concentration of S2 minus stays as 4.2 times 10 power negative 16 molar. So we use the dissociation. You can see that K1 was given, K2 was given. Then we calculate the overall. So this one is the same as this one. It will be cancelled. We calculate the overall equation, overall reaction. Then we calculate also the overall reaction constant. Then we are going to have the K1 times K2. Then we get 1.43 times 10 power negative 20. Then we calculate what will be the concentration of the acid, so that this concentration S2 minus stays as 4.2 times 10 power negative 16. So if you do the expression of this overall reaction, we can see that we have the H plus, which will be multiplied with the concentration S2 minus over the H2S concentration. Then we can replace the value and then find the value, the concentration for the H plus. So if we do the arrangement and the calculation, we will see that the concentration for H plus will be equal to 0.0018 molar. So we need to add the acid so that the concentration of hydrogen does not go beyond this one, because if we can keep the H plus concentration as 0.0018, then we are sure that the S2 minus in the solution will be equal to 4.2 times 10 power negative 16 molar, and we are sure that we are only precipitating the lead without precipitating the iron. So that means we need to add the HCl, the acid, so that we are going to keep the H plus as the 0.0018 molar into the solution, so that you can precipitate only the lead without precipitating the iron. So next time we will see the solubility and the pH.